Hey, good day, folks. Welcome to Bright's Mind Academy, where we bring brilliance to every lesson, of course. Now, in this video now, after now that we have discussed Le Chatelier's principle and how factors such as temperature, pressure, as well as concentration affect now equilibrium position, right? Or the state of equilibrium in particular, okay? Now, in today's, chemical equilibrium is going to be divided into three parts, okay? Actually, I'm going to divide it into three parts. The first one was Le Chatelier. The second one is going to be now equilibrium graphs. Now, the third one that is going to be the most important, okay, it's not all of them are important, but the one that the struggle is the realest, it is now KC calculations, okay? Yes. Now, without wasting any further time, let's now look at this. So now, we're going to be looking at the rate graph. We also have the concentration versus time graph. Okay? Yes. Now, the rate graph, it is the graph that shows you how the rate of a reaction as time goes, right? Whereas the concentration graph shows you how the changes that occurs in the concentration of a particular something, okay? Here it can not only be concentration, maybe it can be number of moles, okay? Number of moles, okay? Yes. Now let's hear what they say here. Okay, let's hear what they say. They say now to us, initially only only reactants are present. Okay, this is what we know. Let me quickly fix. Okay, initially only reactants are present. Initially, only reactants are present. That's true in a reaction. In a reaction, we start with reactants. Then, as they react, that's when we form what? We form products. That's what we generally know, right? And now, as the reactants form now, the rate is higher. Remember from the reaction rate, as the reaction starts now, the rate is higher, okay? And the rate of the forward reaction is higher, okay? Why is it the forward reaction more specifically? Because now the forward reaction is the reaction that causes, remember if we have H2 like that, B2. Remember the forward reaction. Remember we use the product, then after using the product, we form, okay? Now, hence we are saying now, the forward reaction, it is favored. We're gonna say the forward reaction is favored right now. If that's the case now, but it decreases with time as reactants are being used. Yes, indeed, the reaction, the rate will not be high forever. Okay. Yes. Why? Because now as time goes on, the reactants are being used up. Now they end up being used up. Okay. Then the rate becomes slow and eventually comes to stop. Right. So this is what is explained here by the graph. Now that the forward reaction here, as it starts, the rate it is young, it is greater here. Can you see that the rate is greater? But now as time goes on, decreases. Why? Because now there is a decrease in what? In content of the reactants, right? Now, can you see now, as time goes on, the reverse reaction will start to increase. Why? Because now we now have products, right? And remember, in a reversible reaction, remember, this occurs in a reversible reaction and a closed system, right? Remember, in a reversible reaction, the products after being formed, they will try to go back to being what? To being reactants. So now, as this one, the rate of this one decreases, the rate of this one increases until they reach the point where we call, the point that we call what? The point that we call equilibrium. This is what we call equilibrium. And remember, we have two definitions. The one that says now, it is a equilibrium, it is where the rate of the forward reaction, it equals the rate of the reverse reaction. Can you see in this portion? It is what is being explained there. Yes. So now, they say as products are formed, the rate of the reverse reaction increases from 0. Why does it increase from 0? Because initially we did not have any products. Okay. Yes. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. This is the definition of dynamic equilibrium. Remember that? Yes. All right. I want to believe you are following. Now, remember it is a dynamic equilibrium, okay? Yes, hence the rate graph equal, okay, sharp. Now let's go to the concentration. This is just the basic, okay? This is just the basics to. Please take note every time when you look at the graph, the given graph, you look at the axis, what you are given here, okay? Yes. On the concentration, they say now initially there are no, what's happening? Oh. Initially there are no initially there are only reactants, right? That's what we have discussed. And the concentration is high, okay? But decreases as time, decreases as reactants react to form product. True. The concentration is high, starts at a high point, right? But as time goes on, it decreases. The concentration decreases. Why? Because we are using up those reactants. We are using them up, okay? But now, as we are using them up from zero, we have what? We have our products. Products start from zero because initially we did not have them. Then as time goes on, they form now. Here they are. Okay? But now I want you to do something. Can you see from this portion here? Okay, let me do this. This portion here. It is a portion in which what? Now, can you see now the concentration of the forward as well as the concentration of the reverse? Now it is constant. Can you see it is no longer changing, neither decreasing or increasing at this point, even on this point. Okay? Yes. Now let's look what they say. Initially, there is no products, but the concentration of the product increases as the reactants react to form products. Okay? At equilibrium, the concentration or amount of the reactants and products remain constant. Remember, we have two definitions. The first one here, okay, that talks about the rate. The second one that talks about the what? The concentration. So the first one says at equilibrium, the rate of the forward reaction equals the rate of the reverse reaction, okay? And the concentration one says now at equilibrium, the concentration or amount, okay, of the reactants and products remain constant. They are not the same. They are not necessarily the same, okay? They can be the same, but they are not necessarily the same. What's important is that they are constant, okay? Notice how the concentration of products and reactants do not have to be the same as in the case of the reactants graph, right? Hence, when looking at the concentration time graph, we can tell when a system has reached equilibrium by what? By the flat line of concentration graph, by the flat lines. That tells you, okay, now we have reached what? Dynamic equilibrium. Like that. Now, let's now go into more depth about the graphs. Okay. Now, I want to start with this simply a graph, which is the catalyst graph, because now remember there's a catalyst. Oh, take note here. When analyzing a graph, step one is it is to determine the quantities on the axis, meaning now whether it is the rate graph or it is the what? The the concentration graph or moles graph. Okay. Yes. Okay. Now let's look at this graph. Effect of a catalyst. Sorry, what does a catalyst do? Remember, a catalyst does not affect the equilibrium position. Remember, that's what we said. Okay, but what did we say? We say a catalyst now does what? It increases the rate of both the forward and reverse reaction. Okay, a catalyst, it increases the rate of both the forward reaction equally. Okay, I repeat, it favors both reactions equal, meaning it increases the rate of both the reverse and forward reaction. How? Equally. Okay, yes. Now, now let's see. The addition of a catalyst, okay, will favor both the forward and reverse reaction by the same amount, meaning what does by the same amount mean? by the same amount means now, okay, let me do this. Favor both by the same amount, meaning equally. Equally like that. Now let's look at what they are referring to. Can you see now? Okay, the rate of the forward reverse reaction here it is. Okay, then the rate of the reverse here it is. All right. Then at this point here, let me do this. At this point here, equilibrium is reached. At this point here, can you see they are equal? Okay. Now, what happens? Can you see now? At an instant time, whatever time interval here, at an instant time, let's say T1, at an instant time T1 now, the rate of both uh, the forward and the reverse increases. And how equally can you see now they increased from here to here equally so with this by the same amount, right? And then they reach equilibrium at the same time. Okay, so now here this is what we now say at T1 there was a what addition of a catalyst. The easiest graph that you can come across. The easiest graph that you can come across. Okay. Then here again we have the state of what? The state of equilibrium. Okay. Yes. Okay. And now check. Remember what does the catalyst do? It increases the rate. Can you see now the rate is now at a higher position? Can you see now the rate it is now at a higher position, but initially the rate was at a lower position. So remember the catalyst increases the reaction rate. Okay, yes. So this is basically this. By looking at this, they increase both. Even if they ask you reason using the Chatelier's principle, which disturbance was a is indicated by the graph in time t2, you'll say a catalyst, addition of a catalyst. Why? Because now the forward and reverse reaction was favored, okay? Or you can say both the reaction rates increased by the same amount, okay? Meaning both the forward reaction and reverse reaction were favored again and equally so, okay? Yes. Now, they say to us now, when you add what? Of the concentration curve, can you see that we do not have it? Why? Because now a catalyst does not affect the what? The what the the amount that we have. It only affects the rate. Okay. When you add a catalyst to a system at equilibrium, both the forward and reverse reaction speed up, right? So there is no change in the concentration of any species in the mixture. Adding a catalyst will have no effect on the graph of concentration versus time. Hence, you do not have a graph to illustrate the change there. Okay. Yes. So that is clear on the catalyst graph, I believe. They like it on multiple choice, but they can also assess it also on a exam question. Now let's look at the effect of what? Effect of the temperature. Okay. Now, I want you to take note of this. This is the only way you're going to understand this. If you can remember that when we affect the temperature, we do not affect the temperature of the forward reaction or the reverse reaction. We affect the temperature of both of them. Actually, we affect the temperature of the system. Okay, so hence now the temperature will affect both the forward and reverse reaction. Now, let's read the statement here. It says a change in temperature will affect both forward and reverse rates in the same direction. Either both increase or both decrease. Meaning if the temperature increases, it means both the reverse and the forward reaction will increase. The rates will increase. But now what will determine is what will happen. The disturbance is the one that will tell us which one was favored. Okay? However, the effect will be unequal. Indeed, with the endothermic reaction favored by an increase in temperature, and the exothermic reaction favored by the decrease in temperature. This is what we know from our theory of Le Chatelier's principle. Now let's consider a reaction here. Let's consider a reaction there. Now we have NO2, 2 moles of NO2 forming this one, right? Can you see now our change in A sheet is less than 0, right? So it means, remember change in AC less than 0, it is an exothermic reaction. So it releases. It does what? Releases heat. So remember I said when it releases heat, I come and put heat on this side, right? Now let's look what happens when there is an increase in temperature. Like, remember what I said? I said it is the temperature of the system that is increased, meaning I'm expecting to see both graphs to have an increase, but take note, the increase will not be equal. I'm not expecting to see increase in the reverse forward and increase in the reverse like this equally. No. What? Check. What will happen is they are at equilibrium, they reach equilibrium, right? Now, when the temperature is increased now, like the reverse reaction, okay, let me tell you this. I'm going to tell you this. The one that is favored, okay, I repeat, the reaction that is favored is the one that will increase the most, okay, I repeat, they will both increase, yes, but the one that is favored will increase the most. Let me use this so that you understand what I'm trying to say. Okay. Now, let's say there is an increase in temperature. Increase in temperature will come here, right? There is an increase in temperature. Remember what will Chatelier do? Chatelier will try to do what? To decrease the temperature on the right hand side by doing what? By transferring heat to the other side. Can you see now which reaction is favored? The reverse reaction is favored, right? So now the one that is favored, I repeat, the one that is favored is the one that will rise the most. Can you see which one is favored here? The reverse. So I'm expecting the reverse to be the one that has that rises the most. Okay, let's see. This is the forward direction. Sorry, let me repeat that. This is the forward direction. Then after a time, it increases. After T1, there is an increase in temperature. Can you see that? But can you see it is shorter than what? Than the reverse reaction equilibrium. But now at time T1, there is an increase in temperature. It increases the most. Okay? The one that increases the most, even if they did not tell you, they won't tell you which one is favored. They will tell you, Uri, here is the graph. Which reaction is favored? The one that increases the most, okay, is the one that is favored. I also proved it now. Okay? Then check what happens. Then check what happens now. After that portion, then after this one is favored, it will come back to equilibrium. And this will try to go to equilibrium also. Okay? Yes. So now, let's see. If the temperature is decreased, okay? If the temperature is decreased, remember all this effect happening here. We talked them with regards to this reaction, okay? Yes. Okay. Now, if the temperature is decreased, I come here where there is heat, I decrease it. What will the Chatelier try to do? The Chatelier will try to increase the heat on this side, okay? By doing what? By taking heat from the left-hand side and transferring it where? To the right-hand side. Can you see now? The forward reaction is favored. Can you see that? Can you see that? The forward reaction is favored. Okay, yes. Now, check. Here I said the one that increased the most. Check, the word increase correlates with the most, okay? The one that increased the most is the one that is favored. But on this side, we change our statement. Actually, we do not change. We use the correlation. The one that decreases less is the one that is favored. Can you see? Here we say the one that increases more is favored. Can you see increase correlates with more? decreases correlates with less. Okay, so here the one that decreases less is the one that is favored. Let's check if the temperature is decreasing here, the forward reaction will be favored. So let's look and see. Remember, both of them will decrease. Okay, why? Because the temperature of the system decreased, right? Now here it is, the forward reaction equilibrium, reverse reaction, it reaches equilibrium. Then can you see now there is a sharp decrease on this one? Okay, decrease on that one. Then there is a less decrease. Oh, this one decreases more. Okay, then this one decreases less. So, and remember what I said. What I said now, if I decrease this, Le Chatelier will want to go in that side. So it means now the forward reaction is favored. And now I just said now the one that decreases less is the one that is favored. Let's check which one decreases less. Can you see the forward reaction decreases less and now returns back to equilibrium? So it means now in this case the forward reaction is favored. How cool is that? How cool is that? Now let's see what do they say to us here. They say initially the reaction reaches equilibrium. Again, we saw that it reaches equilibrium here, right? Both the forward and reverse rates are equal. That's true, right? Now, okay, the rate of both forward and reverse reaction increases instantly at T1 due to what? Due to an increase in temperature. Okay, can you see the rate of both the reverse and forward increases, but not equal? We did not say equal here. We did not say equal here. And unlike what's this air concentration, where they increase by the same amount, here they do not increase by the same amount. Okay. Now they say the rate of the reverse reaction increases more. The reverse reaction is endothermic and is favored by the increase in temperature. Okay, the fourth reaction is exothermic. Okay, that's okay. That's fine. We'll look at that. Okay. But what's important is that the one that increases the most. Okay, the one that increases the most. Can you see? Increases more, and is the reverse again. The rate of reverse increases more. So it is the one that is favored. Okay. Then they come and say now to us, the rate then changes. Reverse rate declines steadily as products are being used up, and the forward rate increases steadily as the concentration increases until they are at equilibrium again. Okay. And this one, they are referring to this portion here. Okay, what do they mean? They mean now at this portion, we said, Rona, after this part, the reverse reaction will be favored. If the reaction, forward reaction, reverse reaction is favored, this way there will be a decrease on this side. Okay, there will be a decrease on this side, there will be an increase on this side. Okay, hence now there will be what? Decline in the reverse reaction, because now, okay, if this one becomes less, now it decreases, and if this one becomes more, we do what? The rate increases. Okay. So hence now this one, after equilibrium, it increases. Why? Because now they are adding something to it. Okay, on this one it decreases. Why? Because they are decreasing something. Okay, yes. Similarly, this is what they will explain on uh, these graphs. Okay, then the rate of both the forward and reverse decreases instantly. Okay, then the rate of the forward decreases less. Can you see? The rate of forward decreases less. Therefore, the forward is favored. Okay. Yes. So now let's look at the concentration versus time graph. Okay. Concentration versus time graph. Now, in this case, the examiner in the exam room, one thing I know, they won't show you this. Sometimes they won't show you this. They will just leave you like that. Okay. But now they give us. So we say Um, the change in temperature will cause a gradual change in what? In the concentration of what? Of a of species present, right? If the concentration, if the concentration of product increases, that the rate, the reactants, that of reactants will decrease and vice versa. Okay, that's true. If the forward reaction is favored, this one will decrease, this one will increase. If the reverse reaction is favored, this one will decrease, this one will increase. This is what the statement means. Now, initially NO2, it has a certain amount of concentration, right? And it decreases as the reaction goes on, and then it does what? It reaches equilibrium. Okay? Similarly, uh, NO2 starts at zero, okay, it had nothing, then it increases because now they are being formed, then it reaches equilibrium. Let's look at time T1. What happens at time T1? We are told that there is an increase in temperature, okay? Remember, I said put heat on the side. If this is less than zero, it means it is plus heat on that side. Okay? Put heat on that side. How does putting heat help you? It helps you say, okay, there was an increase in temperature, meaning we increased this side. So what will the system do? The system will do what? Will try to reverse that, okay? It will favor the reverse reaction because now if there is an increase, it will say, okay, it's fine. Let us transfer the heat to the other side. Then now what the reverse reaction is favored. Can you see now when the reverse reaction is favored, the concentration of NO2 increases because it is the one that is being favored. The concentration of it increases because we are going to that side, to its side. So I'm expecting NO2 after equilibrium to do what? To increase. Okay? Now, since while we are favoring that one, do you agree with me? Everything in here will decrease. So I'm expecting N2O4 on after equilibrium to do what? To decrease. This is like that. Basically like that. Okay. Similarly here, concentration of NO2, initially it is something, it decreases, and then reaches equilibrium. N2O4 increases and it reaches equilibrium. At time T1, we were told that there was a decrease in temperature. If there is a decrease in temperature, we come here on this side, there is a decrease in temperature. The Chatelet will say, okay, let me go to the other side and transfer heat to you. Okay, you are no longer transferring this time, you are the one who receives. So, okay, we will take energy from that side and transfer it to you because there is a decrease, right? Now, check, if we favor the forward direction, this one in here, there will be an increase on this side because we are favoring that side. We are producing to that side. So there will be an increase on this side. But now, since well, we are taking from there, from NO2 side, NO2 will do what? Will decrease. Meaning now, can you see? After equilibrium, I'm expecting NO2 to decrease. Now, here it is equilibrium. What is NO2 doing? It is decreasing. At equilibrium, what is the product doing? It is increasing because we are favoring its side. Okay? Yes. Now, let's look at the statements here. It says initially the system reaches equilibrium here, right? Second bullet, increase in temperature favors endothermic reaction. Okay? When T is increased at T1, the concentration of the reactant increases rapidly because the reverse endothermic reaction is favored. Okay? Remember, we said if there is an increase in temperature here, we're going to transfer heat to the other side, meaning the reverse reaction is favored. Okay? So now the concentration of the product will decrease as we do that, but the concentration of the reactant will increase. This is basically a summary of what I've just explained. Okay? Mm-hmm. There is a net increase in reactants. Okay, the increase in concentration of the reactants causes the forward reaction to also increase. Okay, yes. Similarly, here initially they are at equilibrium. Decrease in temperature favors exothermic reaction. When T is decreased, temperature is decreased at time T1 here, the concentration of the product increase. Why? Because now if this is decreased, we will want to transfer heat to that side. It means we'll go to that side. Now the concentration of our product increases rapidly. Okay? Because of the forward reaction was favored, but now the concentration of the reactants will decrease. Okay? So yes, this is basically that. This is basically that about the graph and heat there. Okay? Yes. Okay. Okay. Now let's leave that here. All drawings. Cool. We can move now. Effect of concentration. Now, effect of concentration now, this one you will see it is special, unlike the others that you're gonna do. On this one, the one that is affected will either increase. On this one, they do not both increase because they do not affect the system. Okay. The one that includes system, it is the temperature and pressure. Okay. So if you increase the temperature, you increase the temperature of the system. So both of them will increase, but not equally. Or both of them will decrease, but not equally. Similarly to the pressure, both of them will decrease, but not equally. Both of them will increase, but not equal because you affected the system. But on this one, on the effect of concentration, you affect one thing, one species. Meaning if you affect NO2, it is the one that we will see a sharp from. This one we will not see a sharp. We'll just see a gradual. Okay? Let's see. Let's see here. If you are on rec. Okay? What do they say here? A change in concentration of a substance will favor the reaction that decreases the amount of the substance. Okay, this is Chatalia. This will appear as a sharp increase in the rate of either the forward or reverse reaction. Okay, if we do what? We increase the concentration again. The increased rate will then gradually decrease, and the decreased rate will gradually increase until they equal again. This one I'll explain thoroughly. The reading is not for me. We'll see. Let me do this. Okay. I'm gonna need this one. I work well with a vanishing pen. Okay. Now there is an increase in concentration of the reactant, right? If there is an increase in the concentration of the reactant, there will be a sharp increase on the forward direction. Okay? There will be a sharp increase on the forward direction. Can you see now we affected the reactant, right? So there will be a sharp increase on the forward direction because now we affected the reactant, and the reactant we know they go forward, and as they go forward they form what product. So now here they are, they reach equilibrium. Here there was I think when they were trying to dispute this, it cut now. Okay? So it's supposed to be like that. Okay, let me use a pen. Black color. Okay, so here let's rectify that. It's supposed to be from here and goes there like that. Okay, yes. Okay, no, for this one I prefer it. Good. Now the reaction, here is the reaction, here is the reaction. Okay, sharp, here is the reaction. It reaches equilibrium, the forward, right? The reverse also increases and reaches what? Equilibrium. But now there is an effect in something. How we will see that? There is a suddenly a spike, yes, sudden spike in the forward direction. So it tells you now something was increased. So it means there was an increase in something. But what is that something? Can you see if the forward is the one that had an increase, sharp increase? It means now NO2 was added. Okay, there was an increase in the concentration of our reactant. Hence now our forward reaction had an increase what rate. Why? Remember we said what? When you add the concentration, let's rewind back to reaction rate. Ne? On reaction rate, we said now, as you add the reactants, as you add the concentration, you do what? You increase the effective collisions per unit time. Therefore, the rate will do what? Will increase. Hence, now the rate of the forward will do what? Will increase. We will have a sudden spike. This is a spike, okay? But now, can you see now what happens to that of the product? It just casual. But after this sudden spike, what will happen? Now the forward direction will be favored because if this is increased like that, which reaction will favor? Will favor the forward reaction. Can you see now, as you favor the forward reaction, the products increase. And when we increase the product, remember, effective collision will occur more on the product, meaning now their rate will increase. Okay? But on this one, we have a fewer concentration because we are decreasing it. As again, after an increase, which was an effect, Le Chatelier will want to decrease that concentration. As the concentration decreases, there will be fewer collisions per unit time, meaning there will be less what? Reaction rate. Reaction rate will be low. Okay? Let's look at the decrease. Can you see here? They did not increase, they did not both increase, okay? This does not apply on concentration. It only applies on pressure and what? Temperature as well as catalyst, because catalyst is added to the system, okay? Let's look at the decrease in concentration of the reactants. Now, my forward reaction here is it reaches equilibrium. My reverse here is it reaches equilibrium. Now, there is a decrease in the concentration of my what? Of my reactant. Meaning, remember, if I have fewer concentration now, the effective collision, there will be less effective collision per unit time, right? Therefore, what will happen? Now, the rate of the forward reaction will decrease. Okay? The rate of the forward reaction will decrease. Can you see now? Here it is. It decreased like that. It had a sudden decrease. Okay, because now the rate is no longer good, is no longer high. Why? Because now the concentration is less. There are now few what collision per unit time, meaning the reaction rate will be lower. Okay, these topics relate. Reaction rate, chemical equilibrium, they relate. Okay, yes. So now let's talk. After this sudden decrease, after the effect of decreasing concentration of the reactant, what will Chatelier do? The Chatelier will say, okay, I'll ask the other side to transfer concentration to you, meaning I will favor what? The reverse reaction. Now, can you see now the reverse reaction is favored? Oh, sorry. Oh, yes, if there is a decrease in here, the forward reaction, sorry, the reverse reaction will be favored, right? And now, check what happens when we favor the reverse reaction. When you favor the reverse reaction, the concentration on this side will decrease. Okay? If the concentration of the product now decrease, it will affect the rate of the reverse. It means now the rate of the reverse will be low because now the concentration of the product is less. Let's look, if I'm being honest, here it is. Reaches equilibrium, then the rate of the reverse decreases. Why is it decreasing? Because we favored the reverse and now the content in here decreases. But now as we favor the reverse, what happens to the content in here of NO2? The content in here, not the content that of TikTok, the content like what it contains. It then what increases. Okay, remember initially it was decreased, but now after being transferred thereof, it will try to increase and reach equilibrium again. Therefore, the forward reaction will increase like that. Okay. Check. If the reverse reaction is favored, it does not mean it will increase. Check what will happen to the product. If the product decreases, it means the rate of the reverse decreases. Okay. But if the product increases, the rate of the reverse increases. Okay, this one correlates with the reverse, this one correlates with the forward. Okay, yes. So now let's see. They say initially the concentration, initially the reaction reaches equilibrium, right? Both the forward and reverse rates are equal. Good. At the instant T1, when more concentration of NO2 is added, can you see concentration of our reactant is added? The forward rate increases sharply. Okay, there is a sudden spike. Okay, as the reactant is consumed in the reaction, the forward rate decreases because now there are fewer reactants to use. Okay, to a constant value. Initially, the reverse reaction is unchanged. Okay, initially. Yeah, it is unchanged. Okay. However, a small product is formed as more products are formed, the rate of the reverse reaction increases to the new constant value. Okay, eventually the rate of the forward and reverse reaction become equal. Again, they will reach what? Equilibrium again. Okay. Similarly, this is what happened. Initially, the reaction they are at equilibrium. Okay. At instant T1, when the sum of when some of the reactants, which is NO2 in this case, is removed, the forward rate decreases sharply. Okay. Sudden spike. I do not like to call it a sudden spike. I like to call it a sudden drop. Okay. Uh, the since the reverse rate is larger than the forward rate, there is initially a net production of NO2. Okay, remember when I decrease this, they'll favor that one and I will produce those. Okay, initially the reverse rate is unchanged. However, since the product is no longer being formed at the same rate, the reverse rate decreases. Okay, yes. So this is basically that. Let's look at the concentration graph. Remember, I said the one that will change, we are affecting, will have a sharp increase or decrease. Okay. Okay. Good. Okay. Now let's look at concentration versus time graph. Okay. Here we have our reaction like that. Cool. Now there is an increase in concentration of the reactant. Our reactant it is what? NO2. So NO2 initially, here it is again. Initially, it is decreasing because it is used up and reaches equilibrium. N2O4, our product increases, reaches equilibrium. But now there is what? Increasing the concentration of the reactant. The one that is increased, it will sharp. It will be the one that sharpens, okay? Because we are adding more to it. Then it will do what? It will decrease. Why? Because we do not want more of it. We want to reach it. Why? We want to reach what? Equilibrium. Can you see that? So we will say, okay, you increase, but that's not what we want. We want you to do what? To reach equilibrium, just so decrease. So, and this one, the reverse will be what? Will increase like that. Okay. So now, similarly in here, they reach equilibrium, then they decrease the concentration of those. Here we decrease them. Then remember, you say, okay, we not want you to decrease. Instead, we'll do what? We'll increase you. Now, same. I say if there's an increase, it means we increase this one, right? Then what will happen? What will happen? Le Chatelier will say, no, I have to transfer this concentration to the other side. You are having more. Le Chatelier says, okay, I'm favoring the forward direction. As Le Chatelier favors the forward direction, can you see now the product of NO2, N2O4? I mean, the concentration of our product will increase. Why? Because we are favoring the side that produces them, right? So hence we are having what? An increase in the concentration of N2O4. But since we are favoring that, meaning we are using more of these, so they will decrease. Hence now after a sharp, they do what? They decrease. Similarly here, if there is a decrease like that, Le Chatelier will say, okay, it's fine, I will transfer some to you, okay? As we transfer some to that side, the concentration of this one decreases. Can you see if that's the truth? Yes, the concentration of N2O4 here decreases because we are favoring the reverse. Now, but what happens is we favor the reverse, the concentration of NO2 increases, okay? Yes. So let's read here. At the instant T1, when more reactant is added, when more reactants are added, the concentration of NO2 increases abruptly, okay? With a very high increase there, okay? The concentration of NO2 begins to decrease almost immediately. Why? Because now as NO2 is consumed again in the reaction, because it is consumed in the reaction, its concentration decreases back to the constant value. Now, but initially the concentration of N2O4 remains is unchanged. They did not affect it again. But now, however, as the equilibrium adjusts, more product is formed and the concentration of N2O4 increases to a new constant value. Because now we favor that reaction, so it means the concentration of these should increase. Similarly to this one, I won't read them, okay? Yes. This is not what you used for reason. They will say use Le Chatelier's principle, okay? This is just explaining to you what's happening, and I already done that. Now let's look at our last graph, which is our pressure graph. Okay, this one will be a nice example I like thereof. I want us to discuss what is which change occurred in those time interval. Okay. Mm. Mm. Okay. Constant. What's happening? The pressure. Remember, on pressure, it is the pressure of the system. Okay, it is the pressure of the system that is decreased or increased. So it means now, when there is an increase, we will see an increase in both the forward and reverse reaction. Okay, this one, it is this graph here. It is the same as the temperature graph. Okay, many people will confuse this. Okay, but it is the same as what? As temperature graph, but we'll see as we do question how we differentiate them. Okay, now a change in pressure of a system will, or can you see, of a system will do what? Will cause a sharp increase or decrease in concentration of all the reactants and product in the gaseous phase. This will have the same effect as the change in concentration, although the increase or decrease will be more gradual. We'll see that. Now let's see if what happens now. There is an increase in pressure. Okay, let me choose this. Okay, now can you see now this one? We have 2 moles in this side, we have 1 mole in that side. So let's agree if there are 2 moles and 1 mole in that side, when there is a decrease in pressure, which side we're gonna favor? We're gonna favor the side that produces more. If we decrease the pressure of the system, we're gonna favor the side that produces more moles. Which one is that? The reverse. Okay, but if we increase it, if we increase the pressure, we will want to favor the side that produces fewer, because we already have more. Can you see? So we want to produce fewer, which is the forward reaction. Let's look now. There is an increase in pressure. Remember, increase in pressure is the same as decrease in volume. Why? Look at my last video. I said pressure, it is inversely proportional to the volume, and I explained why using Boyle's law and ideal gas law. Reaction rate, here it is. Initially, it decreases because we are using our reactant. It reaches equilibrium. Reverse reaction, it increases. We are forming them. It reaches equilibrium. Now there is an increase in temperature. Now both of them will increase. Okay? Both of them will increase. Okay? So both of them will increase. This is 2, this is 1. We want to favor the one that produces what? Less. Okay. So now remember on this one, I still repeat, the one that increases the most is the one that is favored. The one that increases the most is the one that is favored. The one that decreases less is the one that is favored. Let's look. I know here we're going to favor what? The forward direction, because why? It produces fewer moles because there is an increase. Okay, let's look if the graph says the same now. After an increase, they both increase because it is the pressure, right? Pressure of the system increases both the rate, but not equal. Which one increases most? Can you see the forward increases most? So it means now the forward direction is the one that is favored. Is that true? Yes. If this is 2 and this is 1, when there is an increase, we favor the one that produces less. So now the forward is favored, then equilibrium, like that. Okay. Similarly here, decrease in pressure, they will both decrease like that. Can you see? Both decrease, but the one that decreases less is the one that is favored. Let's see. Here, when we decrease pressure, what will happen? We'll favor the one that produces more, which is the reverse reaction. So let's see, is that true? Can you see now the forward reaction decreases more? So remember, we do not use decreases and more at the same time. They do not match. What matches decreases less? Okay, so the one that decreases less, it is the reverse reaction here. it decreases less, okay, then reaches equilibrium. So the one that um, decreases less is the one that is favored. Is that true? Is that the truth? Yes. Can you see when I decrease now, I will favor the one, which one? The one that results in more, which is the what? The reverse. And here the reverse decreases less and is the one that is favored. I want to believe you are following. I want to believe you are following them. Okay? Yes. Good. Now let's see how they explain it. Okay, here there equilibrium, we know. The pressure increases a pressure increase causes an increase in concentration of both the reactant and product, okay? And both the forward and reverse reaction rate increases not equally. Take note, not equally, okay? Since the forward reaction is favored, okay? Since the forward reaction is favored, the rate of the forward reaction increases more than of the reverse reaction. Why? Because 2 moles of gas to form 1 mole or 1 mole gas. Okay, why? If there is an increase in here, we want to do what? We want to go into that side that produces fewer. Hence, now they say 2 moles gas to form 1 mole of gas. Okay, now the rate of the forward reaction increases more than that of the reverse reaction. Both rates adjust to equally at equilibrium, right? Here, similarly, a pressure decrease causes a decrease in the concentration of both. Okay, both the products and reactants, and both the forward and reverse reaction rate decreases, right? Since the reverse reaction is favored, the reverse, remember we are decreasing this, so we'll favor the one that produces more. 1 mole gas to form what? 2 mole gas. This one is a little bit confusing, but just take it as I explain it to you. The rate of the reverse reaction decreases less than that of the forward reaction, and the one that decreases less is the one that is favored. The one that increases more, okay, that increases more is the one that is favored, okay? Hey, just like that. Just like that. Let's look at the concentration graph. They say now a change in pressure will cause all gas curves to change vertically up or down. Up means an increase in pressure, down means a decrease in pressure. Okay. Now let's check. Let's check. Okay. Vanishing pen. Now there's an increase in pressure. Both of the concentration here will increase. Okay. Both. Remember, it is the concentration of the system. Okay. Or number of moles. Both number of moles. Here it can be number of moles. Both number of moles will do what? Will increase. Okay, will increase. But now, can you check which reaction is favored? When we increase the pressure, we favor the one that forms less, which is the forward reaction. Can you see now, as we favor the forward reaction, more NO2 is formed. More NO2, sorry, not NO2, N2O4 is formed. Meaning now I'm expecting the concentration of N2O4 to increase and the concentration of NO2 to do what? To decrease. Is that the truth? Yes. Can you see? Concentration of N2O4, the dotted one, increases. That of NO2, that's what decreases because you're not favoring it. It decreases. Okay? Similarly, when we decrease pressure, both their number of moles or concentration will decrease, right? But now, can you see as we decrease here, the pressure will favor the reverse. Why? Because we are forming more moles. We want to favor the side that produces more moles, which is the reverse reaction. Meaning now I'm expecting on my graph to see the concentration of NO2 to increase, then the concentration of N2O4 to decrease. Is that the truth? Yes. Can you see now the concentration of NO2 here? After equilibrium, after a sharp decrease, not a sharp, after a decrease, it increases. Why? Because we are favoring the reverse reaction that produces the reactant. But now the reactant, since when we are forming the reactant, we are using the product should do what? Should decrease. Okay? Yes, let's look here. At the instant T1, when the pressure is increased, the concentration of both the reactants increased abruptly, right? the concentration of NO2 begins to decrease almost immediately because the forward reaction is favored. Okay. As NO2 is consumed in the reactant, this concentration decreases. Okay. More product is formed and the concentration of N2O4 increases. Okay. Yes. Similarly here, at the instant T1, when the pressure is decreased, the concentration of both reactant and product decreases abruptly. The concentration of NO2 increases. Why? Because we are favoring the reverse. Remember, if there is a decrease, we are favoring the reverse. Now, the concentration of NO2 begins to increase almost immediately because the reverse reaction is favored. Okay. Therefore, as N2O4 is consumed, meaning we are using it to form the products, its concentration decreases back to the what value. So that is that from from the uh, concentration versus time graph when there is a change in pressure. Okay. Now, what I want us to look at it is this one. I want us to tell to do this experiment practical or at this time t. Let me add the t's, different t's here, so that we see at those different time t's which factor was introduced there. Okay. Yes. Let me quickly do that. Check. This is concentration. All right. Now with that being filled up, now let's look at each time interval. Which one is what? Which one is what? Okay. Yes. So now let's look at the at time time t1. Okay, at time t1. Now, as I look at the rate graph, okay, I'll start looking at the rate graph, and now I look at the concentration graph. When I look at the rate graph, here it is equilibrium, right? Okay, that's good. Here I see a sudden spike, and can you see not both of them increased? Only one increased. Remember, I know if only one increased here at time t1, I am very definite at time t1, there was a change, there was an increase in concentration. But of what, I don't know. I know it is the graph of concentration. It is only a concentration that can make the rate graph to only have one sharp increase like that, because I know the pressure, and for pressure and temperature and catalyst, it affects the system, right? So both of them will increase, like maybe like so, even though it is not equal, then there's that. But here, can you see this one does not increase like that? It remains unchanged. So it means here it is concentration. Concentration of what? Let's look at the graph. Let's look at the concentration graph. We know the one that has a sharp spike, it is the one that was affected. Now, can you see? This is the concentration of what here? The concentration of A. So it means now we added the concentration of what? Of A. Okay? Now what will happen? What will happen as we increase the concentration of A? How will Le Chatelier respond? Okay? Le Chatelier will say, okay, you increased here, right? What I'll do now, I'll reinstate the equilibrium by doing what? By trying to decrease this concentration. It means I will favor the forward reaction. Why? Because I'll transfer heat, not heat, the concentration to the other side. Then if that's the case, what happens to A, it decreases, B decreases, C increases, D increases. Okay? We will say now, I can say, therefore, after the Chatelier, concentration of the reactant decreases, and concentration of the product increase. Okay? Yes. Remember the statement that I told you when we are dealing with a KC, not KC, I'm sorry, Le Chatelier's principles video. I said only temperature affects KC value. So now it means here, how will be the KC value? The KC value, the KC value, the KC value will not increase or decrease. It will remain the what? Constant. It will remain constant like that. Why? Because the effect here was not a temperature. Okay. Now let's look at time T2. Remove fish. Let me remove that. I'm done. Now let's look at time T2. At time T2, what happens? There is a decrease, a spike, a sharp decrease. Okay, but can you see it only decreases? Only this one decreases, right? Only the forward graph decreases, right? So it means here they decreased the one of the reactant, right? Let's look which one. Let's look which one. The one that decreases. Can you see that is this one? Okay, but can you see here it decreases like that, and these ones do not decrease hampe like that. So it means now there was a what? time T2, there was a decrease in concentration of B. What will Le Chatelier do? Now, when we decrease, as we decrease B like that, we will favor which reaction? The Chatelier will say, oh, okay, they are running out of, the products are running out of concentration. Well, how about we transfer to them? Okay. So when we transfer to them, there is a decrease in what? In concentration of these two. So the concentration of these two decreases, whereas the concentration of these two increases. Okay. So we'll say the concentration of the reactants, I'll say of the reactants increase because we are favoring the reverse, whereas of the pro, that's what decrease. Kc value remains constant. Why? Because it is only affected by temperature. Let's look at time T3. Time T3 now, there is a what? A sharp increase again. Okay, but now can you see the sharp increase comes from the reverse? Can you see? Can you see the dotted line comes from the reverse? So it means now there was an increase in the product. Okay, the sharp increase in the reverse means there was an increase in the product. Let's see which product was then increased. Can you see here? Okay, it increases like that, it increases like that, it decreases like that. But can you see here? There is a spike, a little bit of a spike that is not necessarily visible. And I want to believe now you are following, right? There is a spike there before. Can you see this one? There is no spike, it just does this gradually. But this one, there is a spike first. It does not, if, can you see now it decreases? So it does, if it was decreasing, it should have decreased like that, but it started by increasing before decreasing. So now the concentration of what? Of D was increased. Increase in concentration of D. Let me minimize this. Then what will happen? What will Le Chatelier do? Now, let's see. If D now, let me remove this. If D now is increased, if we increase D, the Chatelier will say, no, you are having more than enough concentration. How about we transfer it to the other side, like that? Okay. After doing that, you see now these will increase, these will decrease, this one will decrease. So it means now the concentration of our reactants will increase. Therefore, those of our products will decrease. Therefore, Kc value will remain constant. Let's look at T4. What happens? At time T4 here, as I look very carefully, if I zoom out here, at time T4, both of my rates decreases. Okay? Both of my rates decreases. And I know it can either be temperature or what? Or pressure. How do I check that? I say, I saw a decrease in something. Okay? Let me look more the number of moles in this side. On this side, the number of moles, there are 3 moles. On this side, there are 4 moles. Let's look at the graph, which one was favored. Okay? Oh, another thing, remember the change in H, it is less than 0. Change in H is less than 0, it is exothermic and it releases heat. So on this side, I like to add heat. Okay? Now, let's see. Let's start first. On this one, I want you to use assumptions. Ne? Let's avoid the concentration graph a little bit for now. Let's concentrate on the rate graph for now, right? First thing first, because on an exam, they will never give you both of them. They give you only one. I want you to analyze this one. Now, let's look at the rate graph. Can you see now, where are we? Or at time T4. Time T4. There was a decrease in the pressure or temperature of the system. I'm not so sure yet, but we're going to confirm with you. Let's assume that there was a decrease in pressure. If there is a decrease in pressure, it means now the reaction that will be favored is the forward, the one that produces more. Okay, that produces more moles. Okay, then now it means now the forward direction will do what? Will decrease less. Again, remember for pressure and temperature, the one that decreases less is the one that is favored. The one that increases more is the one that uh, is favored. In this case, there was a decrease, right, in pressure. Ah, let's assume, let's assume, first try, we try that there's a decrease in pressure. Okay, the one that decreases less is the one that is favored. Which one is that? Can you see? The one that decreases less, can you see that it is the red line? And the red line is for the forward. Okay, the forward uh, decreases less. So it means the forward direction is favored. And we can see here, in this case, what we just did, it proves that what we just did here agrees with this thing here. Okay, so now, in this case, I want to believe it is what? A decrease in pressure. Let's prove using heat temperature. Why is it's not the case? Now, if there is an increase in, remember, they told us changing H is less than zero, okay? And now there, if changing H is less than zero, remember, it means the forward reverse, the forward direction it is exo, the reverse it is endo. Remember what is a decrease in temperature fever? A decrease in temperature favors exothermic. Okay? A decrease in temperature favors exothermic. Let's see. Here, now I'll say now there is a what? There is a decrease in heat. Decrease in what? In heat. Okay? If there is a decrease in heat like that, if there is a decrease in heat like that, which reaction will be favored? We will favor the reaction that wants to do what? We will transfer heat to that side. So similarly, we are also favoring the forward direction. Okay? Decrease in temperature. We are also favoring the forward direction. This is my second condition. Okay? Now, is that the case here? Yes, the forward direction is favored because it's the one that decreases the most. So here, decrease in temperature, both of them are correct. Now, that's when we use what? We use our concentration to do what? To confirm. Okay? To confirm. Okay? Now, let's see here. Let's see here. Can you see now the concentration of A decreased? Okay? It decreased. Similarly, the concentration of B decreased. Why? Why did they decrease? Why did they decrease? They decreased because now there was a what? There was a change. The forward direction was favored, right? But can you see now they decreased the most? Can you see they are the ones that decreases the most? Okay, these ones are the one that decreases the most. Okay, so it means the effect there was more effect on this side than on that side. Okay, let's look here. Here there was a what? They decreased a little bit. I want to zoom out here. Let me zoom out here. They decreased a little bit, then they increased. They decreased a little bit, and then increased. It means now what's this? The product decreased less. So now the question is, which one of the two between the pressure and temperature is now uh, the correct one in that case? Which one is the correct one? Okay, you have decided, right? Now, the correct answer in this case thereof, it is now pressure. The pressure was the one that was decreased. Now, why? Why Mpo is saying now the pressure is decreased? Because now I thought maybe it was temperature. Because now, remember, a decrease in pressure, we will come to this side, okay, where there is fewer number of moles. But remember, the system will do what? Will do what? Will go to the side that has what? That has more number of moles. Okay. When there is a decrease in pressure, we go to the side. We, Nalwena, me and I, we go to the side with fewer number of moles. But Le Chatelier will go where? To the site that has fewer number of that has greater number of moles, that produces number of moles. Hence now in this case, our products, so our reactants decreases the most. Okay. Hence now our product decreases the most. Okay. And now another thing I want you to take note of: when the effect that's taking place there is pressure. I'm teaching you. When the effect that's taking place there is pressure, you will see spikes in the concentration, whether sudden drop or sudden increase. But when we talk about temperature, if temperature was the one that was uh, affected here, it wouldn't affect the concentration of the reactant or product like this. They wouldn't have a sudden drop or sudden spike. They will just decrease. If they are decreasing, they will just decrease like this. Okay, this one they will just increase like that. Okay, but now since while it is pressure, it affects the concentration. Okay, since it affects the concentration of the one is that is not favored. Remember, what is favored here is the forward direction, or the forward direction is favored, right? Therefore, there will be a sharp or a rapid abrupt decrease in the concentration of what? Of the product, because of the reactants, because now we are favoring them the forward. And now this is the disturbance. They will do what? They will increase like that. The reactants will decrease, sorry, and then the products will do what? Will increase like that. Okay. So now let's see if there is a what in temperature, maybe, that so that I prove what I'm saying. We are saying here there was a decrease in what? In pressure. So let me say decrease in pressure or increase in volume. Still the same thing. Therefore, if I decrease the pressure, remember I favored the forward direction. So it means the concentration of the reactant decreased, and the concentration of the products did what? Increased. But the Kc value remain constant. Remember, I only affected the what? It is only affected by the it is only affected um by temperature. Yes. Now let's look at T5. Let's look at T5. Okay, T5. This is exo. Why am I saying the top one is exo? Because remember, this one tells you the information about the forward direction. So it tells you the forward direction, it is exo. So it means the reverse direction, it is endo. Yes, like that. Okay, yes. Okay, now at T5, is it T5? Yes, let's see. there is a both increase. There is a both increase in uh, the rate of the forward as well as the reverse, right? Mhm. Now remember, what did we say? We say the one, if it is like this, it's either temperature or pressure, right? But we say the one that increases the most is the one that is favored, okay? The one that increases the most is the one that is favored. Which one increases the most is that of the reverse. Can you see the dotted lines? Yes. So now it means now the reverse reaction, it is favored, okay? Mhm. The question is, was there an increase in pressure or temperature at this instant? Okay. The question is, was it an increase in temperature or pressure at this instant? Let's see. Let's first assume that there was an increase in temperature. Okay. Remember, if there is an increase in temperature, this is the one. Okay. What will Le Chatelier do? Let me do this. If there is an increase in temperature, this will what? It will increase. Le Chatelier will do what? Le Chatelier will do what? Will try to transfer the heat to the other side. Okay. So now can you see also endothermic is the one that is favored, the reverse reaction, which is endo in this case. And you know that an increase in temperature favors endothermic. So now the reverse is favored. And now we just said here, the reverse is favored. Okay. Mhm. So, okay, cool. Second assumption. Second assumption. Let's assume that let's assume that the pressure is the one that is increased. If that's the case, remember both of them will increase. Both the rate will increase, right? But now, if we increase the pressure, now we come to the side with number of moles, then Le Chatelier will go to the side with fewer number of moles, meaning now the reverse reaction is also favored. So now the question is, which one is which? Because both temperature and pressure are the same. We come to the concentration graph. Can you see now at T5? Or remember when we favor the reverse reaction now, uh, the concentration of the reactants will increase because you are favoring that side, but the concentration of the products will decrease, right? Mhm. Now, can you see now the products are increasing, the reactants are increasing, the products are decreasing. And can you see there was no sharp decrease or increase here? There was no sharp increase or decrease here in the concentration, meaning now, this is temperature. Why? Because now we saw that if it is pressure, they are the ones that decreased the most. Can you see? We saw spikes there, spikes in the decrease, spikes in the decrease of the concentration. So here they just increase and decrease like hamnati fela, like that. Okay, so yes, if that's the case, it means it is what? It is temperature. Hence, now when I explained here, I said it is pressure because if it was temperature, it was going to decrease. Can you see at the end it decreased? So it was going to just decrease like that, decrease like that, increase like that, increase like that. Okay, so here it is what? Temperature instead of what? Of pressure now. Okay, this is how we confirm. We said time T5, it is decrease in increase in temperature. Okay, meaning our reactants will so if I increase the temperature, which reaction is favored? I favored the time T5. I favored the reverse. So it means that our reactants will increase, okay? Then our products will decrease like that. Kc value. Let's talk of the Kc value. Okay, for now you do not know, how does Kc value get affected? But the Kc value Okay, Kc expression, it is concentration of products divided by the concentration of reactants. This is the Kc value. So now, how is it going to be affected? Is it going to increase or decrease? Now let's see. What happened to the product? The product decreased. So if the product decreased, remember Kc is direct. Can you see now Kc is directly proportional to the product? So it means our Kc will decrease. Okay, and the reactants increase. And if they increase, they remember Kc and the denominator is inversely proportional. So they decrease. It means now the Kc will decrease in this case. On T6, the temperature was decreased. Then we will form less reactants. I do not want to go through that. The video is already long, but you will. I'll give you a chance to look at it. Okay. Okay, let me do that. There was a little bit glitch. Okay. Let me do that. Okay, and yeah. Here there was a decrease in temperature. T6, I'm saying there was a decrease in temperature. Can you see? Yes, decrease in temperature, and we favored the one that decreases less, which is the forward reaction. So if you favor the forward reaction, or the one that decreases less, it is the what? The forward reaction, okay? So as we favor the forward reaction, remember we're using reactants. So they just decreased, they just increased the products, okay? Now, how does this affect Kc value? Kc value, remember Kc expression, it says products divided by reactants. The next video will be on Kc value, do not worry. So if I increase the products, it means I'm going to increase the Kc value. So Kc value, that's what in this case it increases like that. Last one before we wrap up the lesson. What will happen at time T7? What happens? Can you see now at time T7, both the rate of the forward and reverse reaction increases. But how? Equally. How? Where do we see this when they both increase equally? We see this if there is a what? There is addition of a what? Of a catalyst. If there is the addition of a catalyst here, we see that like that. So can you see now? Addition of a catalyst, then they reach equilibrium. Remember, what does a catalyst do? It increases the reaction rate. Can you see where was the reaction rate? It reached equilibrium here. But now, can you see after addition of a catalyst, the reaction rate is now high? Because remember, what does a catalyst do? It speeds up the reaction rate, okay? So here, number 7, just straightforward, it's the addition of a catalyst. Time, or here, add catalyst. What will it do? It will increase. It only increases the rate. It does not affect the concentration. Again. Then the Kc value, what will happen? It will remain constant. It is only affected by temperature. Now let me erase this and check whether we are correct or not. Okay, let me do this. Now I can remove here. Sorry. Delete. Now let's confirm. I did not want us to go through this. I wanted us to understand it. Disturbance here, time T1, concentration of A was added. All right? Was added. Good. What happened to the product? What happened to the product? The product then, okay, they did not show you the disturbance. But now can you see C is a product. C is a product, it increased. And we said the product will do what? Will increase. Can you see that? Indeed. Then, which reaction was favored? The fourth reaction was favored, yes. Oh, I did not mention that here. But we can see that, yes, if here A was increased, so we favor the forward so that we decrease it again. So now can you see now Kc is constant, 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 constant. It is only affected by what? By temperature here. Okay, yes. Here at time t7, rate of forward and reverse increase equal. Can you see that? Can you see now the concentration after a catalyst was added, it is not affected? Yes. So you can screenshot this. Actually, let me do this and give you, maybe you can screenshot this in case you want to use it for future reference. Okay, yes. You can screenshot this so that you see for future references what happens. Can you now see here at T4, the one that was a little bit tricky? It was a what? The pressure was decreased. Okay, can you see that? Yes. And Le Chatelier did what? Increase the pressure. Okay. Okay. So yes, thank you very much, folks. That's all for today's lesson. And now on chemical equilibrium what graphs. I hope you enjoyed, and please do more questions based on the graphs, based on reasoning using the Chatelier. Okay, it is the only way in which you will master this topic. Okay, remember practicing, practicing, practicing is the only way in which you will master something. Okay, so thank you very much, folks. If you feel like maybe I should have explained something in a different way, please leave that in the comment section. Okay, yes, remember, I'm trying to assist. I'm not saying I'm the best. You might know this, I might teach you this, and you might master it more than me, and this is what I want. Okay, yes, thank you very much, folks. Until we meet, let's meet again on the next video, where we'll be discussing Kc calculations. Thank you.